Because we have these parameters, we can actually look at limits. So if we look at the limit of very high damping to inertia, that means we can basically ignore inertia, or very high rotation to gravity, we could ignore gravity, or very high gravity to rotation. So there's all kinds of different limits that we could look at. We'll look at the overdamped case, or the case of very high damping compared to inertia. Let's look back there. B is down here, the denominator. So if you imagine B is very large compared to M, B is much, much greater than M times square root GR. So that means epsilon much, much less than 1. We can consider the limit epsilon goes to 0, which is kind of interesting. If we consider epsilon goes to 0, then we have this term on the left-hand side, 0. 0 times whatever that second derivative is still 0. So epsilon second derivative goes to 0. So the left-hand side of the equation goes to 0. So we're left with the overdamped, means really high damping, overdamped limit. And that equation, rather than being second order, is just first order. This ODE up here, if I set that the left-hand side equal to 0, I'm just left with a first order ODE, which is what we've been studying. I'll write it this way: sine theta gamma cosine theta minus 1. I will refer to this right-hand side as f of theta. It's a first order but nonlinear ODE, and theta lives on the circle. Theta goes from negative pi to pi. I can plot what d theta d tau is as a function of theta. The only types of behavior are there are fixed points and their trajectories monotonically heading towards or away from fixed points. That's it. So now that we have a first order ODE, we can use the techniques. Let's just plot on this axis theta, on this other axis d theta d tau. That's the non-dimensionalized velocity. Gamma is the main parameter. So we could look at, what if gamma was 0? If gamma is 0, then we're just left with negative sine theta, pi and negative pi, and we'll plot negative sine theta. This is f of theta with gamma equals 0. So that gamma equals 0 means omega 0. So that means no rotation. No rotation. I've got a fixed point at 0 and at plus or minus pi, which is physically the same place. Let's plot down here, gamma equals 0. What do we have? Let's interpret this in terms of where are these fixed points of the hoop. Well, there's one at the bottom, that's theta equals 0, and then there's one at plus or minus pi, which is physically the same thing. Plus or minus pi are the same point. And if we use our method of figuring out what direction the flow is going that way, and it's going this way. So things are going towards the point at the bottom and away from the point at the top. So if we use the way we've written things before, we'd make that an open circle. This is a filled circle. So for no rotation, this makes sense. And high damping, things will just go to the bottom point of our hoop. So I have a hoop, right? Things just want to settle down at the bottom. That's no rotation case. As I increase rotation, if you think of what's happening at the origin, the plot will be shifting from being a slope of -1 to being flat and then going up. That the critical point would be at gamma equal 1. So if I were to plot that, so this is gamma equal to 1. And if I do gamma greater than 1, then I've got a situation like this. So here's gamma greater than 1, right? Just from plotting things. And then now what direction are things going? There's a little region where things are moving away from the origin. Let's try plotting gamma greater than 1. Here's my absolutely perfect circle. The origin actually becomes unstable. The top point is still unstable. And there's these two stable points on either side of the bottom. If you work out where those are, we get two new stable fixed points. And notice the bottom point went from stable to being unstable. Where are these at? So this is, right, you set d theta d tau equal to 0, and the new points are at inverse cosine of 1 over gamma. That only has a solution when gamma is greater than 1. So theta star, let's call them plus and minus, plus minus that. This is theta star plus, this is theta star minus. And if we were to summarize with some arrows showing how things are going, if we started with the bead near the bottom, the bead will actually move up and go to one of these side stable points. And of course, the top point is still unstable. It's the top point, it wants to fall down. If the picture doesn't convince you, you could do a linear stability analysis and find and classify the fixed points. So this is gamma is greater than 1, we'll call that the high rotation regime. If gamma is less than 1 but greater than 0, that's low rotation and still qualitatively looks like the no rotation case because no new equilibrium points showed up. If we were to talk about the fixed points, those are the places where this formula E theta d tau equals F of theta. Those are the special points theta star that make F equal to 0. So there's two categories. We already could see graphically, this is F theta is sine theta, gamma cosine theta minus 1, just repeated from up there. So sine theta star equals 0 when theta star equals 0 or theta star equals plus or minus pi. So we have the bottom of the hoop and then the top position. The other case would be when gamma cosine star minus 1 equals 0 or theta star equals plus or minus. Inverse cosine 1 over gamma only defined for gamma greater than 1. Now we can do linear stability analysis of these. So those are the fixed points. The linear stability analysis for these one-dimensional ODEs was you take the derivative, you take the Jacobian. For Jacobian one-dimensional things are easy. This is df d theta, which I'll just call that f prime. So it's the derivative with respect to its argument. And this was f up here, so just take the derivative and collect some terms. You will get gamma cosine squared theta minus sine squared theta minus cosine theta. So for the two types of points, right, f prime at 0 is gamma minus 1. So this is less than 0 for gamma less than 1, which meant, if you remember, that means stable. So the slope is negative, stable. And this is greater than 0 for gamma greater than 1, which implies unstable. And you could look at f prime at plus or minus pi is gamma plus 1, which is always greater than 0 for all gamma. So always unstable. And then the other 2 points, if we look at those, what do we get? It turns out you'll get 1 over gamma minus gamma, which is less than 0 for gamma greater than 1, which is the only time when these things exist. So always stable when they exist. It's looking like gamma being the only parameter, it's a bifurcation parameter, and we could summarize our results in terms of a bifurcation diagram. So let's do that. Bifurcation diagram with gamma as parameter. And if we summarize this, that's pi. That's not theta, this is gamma, bifurcation parameter. This is the location of fixed points. So we could plot, plus or minus pi, it's the same the whole time. It's always unstable. Theta equals 0. The down position is actually stable till we reach a certain point, that bifurcation point. Gamma equals 1. And then theta equals 0 becomes unstable and has a parabola that's surrounded on both sides by stable points. So this is looking like a pitchfork diagram. In fact, it looks like a supercritical pitchfork diagram. Supercritical means all the stuff happens after, in this case, stable, middle stable branch becomes unstable, but is surrounded by two stable points. This is the supercritical pitchfork bifurcation, which means you might wonder if this is all true. If I were to just zoom in on some region around where the bifurcation happens, do the dynamics look like the pitchfork bifurcation normal form? If you recall what the normal form was, the normal form for the supercritical pitchfork bifurcation was x dot equals rx minus x cubed. So can we put our system in this form? Yes, we can. Locally, that means just in a neighborhood of that bifurcation point. We need to have the Taylor expansion of sine theta and cosine theta. If you don't recall, I'll just give it here. Sine theta, I always remember the first term because it's theta. The second term is a little bit harder. Theta to the third over sixth. And then I know, there's only odd numbered terms. So just remind myself, it's order fifth and higher. Cosine theta, it's good to remember these, at least the first two terms. This is 1 minus theta squared over 2. And then the next higher order term is, it's only even terms, so it'll be theta to the fourth. So we can now take sine theta times gamma cosine theta minus 1. Remember, that's what f of theta was. And this can be written using these Taylor series expansions as gamma minus 1 theta minus gamma over 2 theta to the third minus gamma minus 1 theta to the third over sixth plus some other terms of order fourth and higher in theta. There's no second order terms. And this is, of course, near theta equals 0, which is where the bifurcation happens. This was f of theta. So we've got d theta, d tau equals, and now let's collect terms. We got gamma minus 1 times theta minus 2 gamma over 3 plus 1/6 theta to the third. And we just ignore everything else. So we say this is for small theta. Time can be rescaled again to make this equal to theta prime equals r theta minus theta to the third. So we've somehow done a rescaling of time so that this term is equal to 1. And now that parameter r is gamma minus 1 over 2 gamma over 3 plus 1/6. In any case, it looks like the normal form. So locally, it looks like that, and it had to. If you're trying to visualize, what does this look like? This is showing beads at equilibrium for a variety of speeds, starting at the top left of no rotation, and then going down to the lower right that's spinning the most rapidly. So you can see some bifurcation point was reached between the top right and the bottom left. Now, this doesn't show the dynamics, but wherever things are released, they're just going to go to the stable state, one of the two stable states. Physically, like I said, there's no experimental realization of this. This is a spinning pendulum. I don't know if I can write on here, can I? So this is a pendulum. This thing, I'm looking at the right side. This thing, there's a pivot through here. So it's like a planar pendulum. but you can rotate this planar pendulum very quickly, and it becomes, physically, it looks exactly like the bead in the rotating hoop. It's like the pendulum, as instead of the middle of the hoop, there's the pivot for the pendulum. So if you get this spinning fast enough, there'll be some kind of equilibrium where this is sticking out to the side by some angle. So physically, same as rotating planar pendulum, sometimes called the whirling pendulum. Give you a physical thing that's been used. These were used for a long time for steam engines. It's called the Centrifugal Flyball governor, and it was a mechanically based feedback system. I think it was invented by James Watt, from whom we get the measure of power. Measure of power, that sounds pretty awesome. He made this thing that to control the amount of steam or any kind of fuel, let's say, going through a valve, the amount of steam actually powers some spinning thing. So the engine, this is the intake valve with this kind of cool looking arrow. That kind of curves in and curves out. I wonder if this is from like the patent. Anyway, so this goes to an engine that then spins, right? Makes some spinning. And part of the spinning using gears and stuff goes to spinning these two balls that, as it spins faster, will go further apart, but gravity wants to bring them in. Beyond a certain critical rotation rate, there's actually a stable equilibrium here. And you get to set what that stable equilibrium is using various knobs to get the engine to be at a certain speed. So this was a way of mechanically achieving that. It ends up that if you model this system, it looks very similar to the bead in a rotating hoop. Like the dynamical equations of motion look basically the same. And you can kind of understand why. This looks like two pendula, equal pendula that are spinning about a central shaft. There's going to be centrifugal forces will push these away, gravity pushes them back, and at some point there'll be some balance achieved if you're beyond a critical rotation speed. There's a diagram of the thing. Like this is fully open, and that's like this. You can adjust things so everything's connected. To really model this system accurately, you need 3 dimensions, so it would be a 3-dimensional system. But hopefully you get the idea. And then here's one of these things in action. It's in the middle. Like this is an old steam engine, I assume from, I don't know, some kind of antique machine show. And so it's right there in the middle. It's maybe hard to see. Like there they are, flying around, controlling this engine.